Hello everyone, my name is Yonzon, and today I'm going to show you how we were able to detect clouds in satellite images. So in coordination with Lockheed Martin, the map department at West Point, we had this problem. We're like, can we take a satellite image and can we detect if there's a cloud or ice in the image? And at first I was like, this is going to be an easy problem. Like, it's just the image. 5 runaway slides. It's just the image. We could do this, but if you think of it, clouds and ice are both white. So inherently, it's a difficult problem because they're amorphous shapes. And as a naive undergrad student, right away, I was like, you know what, let's go talk, let's grab our artificial neural network, because that's what I just learned in my undergrad intro to a machine learning class, and let's use that. And let me just remind you, so artificial neural networks, we have the input layers, hidden layers, and the output layers. And the hidden layers, that's where all the magic happens. That's your nonlinear transformations. And right before you hit your activation function, which is usually a sigmoid or a linear rectified unit, you can classify something. So you could classify things in an image. And this is exactly what's happening in the artificial neural network I just mentioned. But the first thing you do when you're using an artificial neural network is you take this image and you take all the pixels and you put it in a column, or you take the matrix of pixels and you put in a column matrix or a column vector. And by doing this, you ignore a big assumption, and you ignore the vertical and horizontal, like the space, you ignore the horizontal and vertical relationships between the pixels, which is very important when we're trying to detect clouds and ice in the image. And so instead, we relied on convolutional neural networks, also known as CNNs. And CNNs actually maintain the integrity of the spatial features in an image. And what it does is it takes a kernel, which is shown in the orange in here, a matrix of kernel, a matrix of weights, and it overlays it on the image, which is shown on the green, and it does a dot product. And it does this, and it extracts different features from the image, and it creates something like we call a convolved feature. And we do this over and over with multiple layers, and we can extract different features. And then using image segmentation, we can again portray it back on the image, making regions of where we're trying to classify. In our case, we can classify if there's a cloud or there's not a cloud. And this is exactly it being done on a house right here. So this is extracting different features with using the convolved feature map. As you can see, different features have different level of features, and sometimes with different features, we can get high level of features. And so we turned to CloudNet, and CloudNet was a model created by Fraser University researchers. And essentially, it is a CNN using an architecture called UNet. And what UNet does is it has a contraction path and an expansion path. And in this contraction path, which is shown in blue, it takes all, extracts all these features, as I mentioned before. And in the green path below, what it's doing is it's basically taking those features and portraying it back on the image, showing where there's clouds or no clouds, or ice in this example. And we take this model and we use different metrics to improve it. And I want to highlight one metric in particular, and that's the Jaccard coefficient. The Jaccard coefficient is important because this is our loss function. It's also known as a similarity index. It's essentially the intersection over the union. And this is important because when we're looking at our ground truth and our prediction, we can say, are these two things similar? So what we do is we take the complement of this and we're trying to minimize this. This is what we use as our loss function. And so researchers have done this before, and they've done this on the Landsat 8 data set. And this is exactly what I mentioned before, but we have an image shown on the left. This is the natural image, which shown to the human eye. The ground truth is on the middle, and then finally the prediction is on the right. And then below is the average predictions, or I'm sorry, average metrics on this data set. We're saying, can we do this on a different data set? And particularly, we want to use the GO-16 data set, which was which is a satellite launched in 2016 by NASA. And the reason why I wanted to do this is because it has inherently different bands. And particularly in this data set, Landsat 8, it has the green, red, blue, and infrared. But when we get to the GOES data set, we only had green, red, blue, and infrared. So now we're taking less information. We're like, hey, can we still use a CNN to detect a pattern in this image? So shown on the left is the false color image. So this is what we see to the human eye in the top left. And we're saying, can we take this image and make it look like the image below, which is the black and white image below. And this is basically a binary classification, white for clouds, 0 for no clouds. And this is our data set. So it's a GO16, and we took full disk images, 2 full disk images. And we took one on the 1st of last year, so January 1st of last year, and then finally 10 days later on the 11th of January last year at 18 hours UTC. And now once again, we're examining the red, blue, and near infrared bands. And this is what the data looks like. So we're taking this data set and these full disk images and putting it in different bands. And we're saying, can we take what we see on the right, the 3 globes on the right, can we take those 3 things and make it look like the left? And so in order to do this, we cut it up in different pieces. And so we made 368 different patches. And as you can see, this is what one patch looked like. And we're like, okay, with one patch, can we make all these patches look like the right patch? And we found out that we can. So like blending our loss function that I mentioned before, the Jacquard loss, we found after 150 epochs, we were able to get a Jacquard loss of 0.1. So this is pretty good. And how good? Well, here are some examples of how the cloud net operated on the GO16. As you can see, on the left, we have our predictions. The middle is the ground truth, and the right is what is shown to the human eye. So this is really, really close to being quite accurate. And how accurate? Here are the metrics for these specific images. As you can see, they all have high accuracy results, but some of them have low Jacquard coefficients. And this is why we're relying on the Jacquard coefficient, because we really want to see what is similar between the 2 images, the ground truth and the prediction. And then going into our average results were quite good. So the Jacquard coefficient was 83 and our accuracy was 89. And of course, we use other metrics, but these are the 2 main metrics that we're using to update our architecture and make decisions moving forward. So what now? So we have to continue to train in epochs. As you saw in that loss graph, we had a lot of fluctuations. So that shows that we do have room for epochs to train longer. So 150 epochs, that's about 8 seconds each per epoch. So that's 3 hours. So it's computationally, it's costly to do all of those epochs. Finally, we want to train on separate channels to understand the effect of each channel. So we want to see, hey, does one band have more effect than the other? Finally, we want to highlight the false positives and false negatives to see exactly where our model is failing. And finally, and then secondly, we want to train on more imagery, of course, to make sure we can generalize it to a larger data set. And then finally, we want to identify areas in the satellite imagery where there's ice, so we can incorporate that ice and answer that initial question. I will have a poster and I can talk all about the specifics. Thank you very much.